the network economies, SRITE, TNE. He experienced two academic postdocs in Europe and in USA. In the USA, he worked as a research scientist with Professor Rodney Nelson in the Human Language Technology High LT Lab at the University of North Texas, USA. During summer 2014, he worked at James Pennebaker's lab, the University of Texas Austin, as an invited researcher. Earlier, he spent 1 year working as a European Research Consortium for Informatics and Mathematics (ERCIM) postdoctoral fellowship at the Norwegian University of Science and Technology (NTNU), Norway. He also worked for industry before moving to the USA. He worked for Samsung Research India, Bangalore as a chief engineer. He earned PhD engineering from Jadavpur University, India. During his doctoral study, he worked for an Indo-Japan collaborative project entitled Sentiment Analysis, where AI meets psychology. With that, may I request you, sir, to kindly start your keynote presentation.
Thank you, Sachi, for the detailed introduction. Thanks for it. So let me share my screen. Is it visible?
Yes.
Yes, sir.
Yeah, thanks. So I was talking about language models. So this is a typical uh, course I used to cover in Triple IT while I was teaching natural language processing. So language model is possibly everywhere. If we look at NLP world today, and the modern language processing using neural networks and etc. being possible for these three gentlemen, Benjio, Hinton, and Jan LeCun, who got their Turing Award in 2019. And the world of AI and machine learning have changed for their contribution. So I start generally this journey with the saga of these three gentlemen, and then I mean it's a long typical NLP course. I'll not go into the deep of everywhere, but as being told by the organizer Dorinda, that possibly word vector will be covered by somebody else, and the advanced topic of language model will be covered by something else. So what I try to do today is I'll not talk about the high-end things or word vector. Rather, I will be taking you to a journey from where we started back in 60s, and what are the path we actually cover when we reach out to today's language model, and what are the failures, and what people realize from those failures, and how we come to this BERT and GPT era of language processing. So I'll be starting at very basics, and I will slowly build up. So I have 1.5 hours and try to cover as much as I can. So this is about the content, and in my lecture or class and etc. I want things to be interactive. I want people to talk. So many times I will stop, I will ask a question to you, and whether you understand what is your view, what is your perception about this and that. Okay, so try to be more accommodative with me while I'm talking. So let me start at the basics. So somebody ping something. Okay, fine. So machines. So machines do not understand language. So it understands only numbers, 1 and 0. So whenever we talk about natural language processing, we have to understand the language in terms of numbers. Otherwise, machine will not be able to do anything on top of that. So that's the motivation. So with this motivation, people started about talking about language processing since 1950s. If we talk about that 1956 report from where AI actually started, the Minsky's report and so on from the Dartmouth College. So from that day to till today, language processing has been the core of AI for every time. And since language is very personalized, and we have a lot of word forms, we have a lot of language, and one thing could be said in numerous way in a language, and it's being a topic of research and interest for world across researchers. So we in a sense, the NLP community started at very basic understanding how words actually appear. Is there any rule? Can you learn the rule by mathematics? So early two rules were Gibbs law and Hipps law. So let me start with the Gibbs law. It's a very interesting one, and this is the basis of all statistical language modeling before the neural language modeling born. So I could have talked about Gibbs law by myself, but I try to keep my talk as interactive and as interesting as possible. So I'll be showing you one video here. It's a long video, but I'll not be showing you the full one. Maybe for 4 minutes I'll be showing you a video, and then I'll go. So let me start with the Gibbs law. So which actually explain how words appear in the context. Some basic rules.
Hey, Vsauce, Michael here. About 6% of everything you say and read and write is the is the most used word in the English language. About 1 out of every 16 words we encounter on a daily basis is the. The top 20 most common English words in order are the of and to. A-in is I, that it for you was with on, as have, but be they. That's a fun fact, a piece of trivia, but it's also more. You see, whether the most commonly used words are ranked across an entire language or in just one book or article, almost every time a bizarre pattern emerges. The second most used word will appear about half as often as the most used. The third, 1/3 as often. The fourth, 1/4 as often. The fifth, 1/5 as often. The sixth, 1/6 as often, and so on, all the way down. Seriously. For some reason, the amount of times a word is used is just proportional to 1 over its rank. Word frequency and ranking on a log-log graph follow a nice straight line, a power law. This phenomenon is called Zipf's law. And it doesn't only apply to English. It also applies to other languages like, well, all of them. Even ancient languages we haven't been able to translate yet. And here's the thing, we have no idea why. It's surprising that something as complex as reality should be conveyed by something as creative as language in such a predictable way. How predictable? Well, watch this. According to wordcount.org, which ranks words as found in the British National Corpus, sauce is the 5,555th most common English word. Now, here is a list of how many times every word on Wikipedia and in the entire Gutenberg corpus of tens of thousands of public domain books shows up. The most used word, the, shows up about 181 million times. Knowing these two things, we can estimate that the word sauce should appear about 30,000 times on Wikipedia and Gutenberg combined. And it pretty much does. What gives? The world is chaotic. Things are distributed in myriads of ways, not just power laws, and language is personal, intentional, idiosyncratic. What about the world and ourselves could cause such complex activities and behaviors to follow such a basic rule? We literally don't know. More than a century of research has yet to close the case. Moreover, Zipf's law doesn't just mysteriously describe word use. It's also found in city populations, solar flare intensities, protein sequences and immune receptors, the amount of traffic websites get, earthquake magnitudes, the number of times academic papers are cited, last names, the firing patterns of neural networks, ingredients used in cookbooks, the number of phone calls people receive, the diameter of moon craters, the number of people that die in wars, the popularity of opening chess moves, even the rate at which we forget. There are plenty of theories about why language is ziffy, but no firm conclusions. And this video doesn't contain a definite explanation either.
Okay, so let me stop here and let me try to talk to my audience. So Anybody knew about it, Gibbs law? If not, what did you learn? I mean, is it interesting? What we can do with this? Like to hear from audience.
The probability of occurring rarest word is very rare if we follow by this trend.
Absolutely, yes. Any more comments? Please feel free to talk. Any more comment? No. Okay. So let me go back. So we learn about the law. So what is the use of this law? So let us look at the reverse one. So the reverse one says, let's say we have downloaded the whole Wikipedia and we are trying to read, every 1,000 words and trying to, plot how many new words appearing in the corpus. And the pattern will look like something of this sort, the opposite of Gibbs law. So what will happen after a certain point of time, let's say here, so the new word coming ratio will be coming down drastically. And it depends on language. And that's the language that the Higgs law is all about. It says V equal to K into the power beta. Beta is typically square root, sorry, and K is typically 10 to 100 typically for English language. It might be differing, for Hindi and so on. Typically, if we look at English, formal language, it's typically, start getting the flat, 30 millions and so on. So how this law become very useful, in early 90s when people are creating, search engine or, spell checkers or basic machine translation system and so on. So one very, practical example is that, let's say, somebody of you actually working for Google, and the expansion size of Google is 200 GB of, let's say, every 2 months. So what would be your index size table? How many extra cloud you have to put, extra machine you need to put for the index size and so. So possibly you can calculate what would be the new size of your index table and what would be the frequency. So that's become very useful for companies like Google and many other companies who started working towards the content management and so on. So that's become very handy in early 90s. So that's the start of language model. So we started understanding, okay, how words appear or co-appear. Now coming to the more little more complex phenomena of language, we started analyzing language. Let's say part of speech tagging, spelling error, machine translation, information extraction, and semantic role labeling, various other tasks, which cannot be done only by the word distribution, but we have to understand how they actually co-appear, and we have to somehow encode them into some kind of numbers. So people started making vectors out of words. For example, very simple example here, let's say we have a vocabulary of 3 words and we are trying to encapsulate these 3 words by vector representation, 100, 011 and 001. So basically 3 words, and we are just putting 1 if it is appearing. If it is not appearing, then it's a 00. Similar thing people started representing about, is called one hot vector because one place is hot. Similarly, people tried this kind of techniques for documents, 100 and something of that sort. And then people start applying various kind of function like vector multiplication and various algebraic function to process those document and content. Then another gentleman called Firth, he came out in 1957 by saying a very interesting phenomena about language. So the interesting phenomena is, typically word co-appear with similar kind of words. Let me give you an example here. Let me ask a question to my audience. So the question would be, I'll be giving you a word and you have to give me all kind of related words which is coming into your mind just by a second. Okay, so let me start with car. What are the words coming into your mind? vehicle. Okay, you can talk instead of typing. Just switch on your microphone. Road. Okay.
Car, bus, truck.
Car, bus, truck. Fine. Now see, nice examples. Now see, these words are not connected to each other by any grammatical mean. We know these words are connected by our cognitive understanding about the world. So now, in the very beginning, researcher started realizing only the distribution will not help us. We have to understand the relation between words in some or other. So obviously there are two paths. Whenever we start talking about NLP, there are two paths. Some people took the linguistic path of understanding the linguistic structure, what did have been built, and so on. And some other people who actually believe in mathematics, they started formulating mathematical model out of it. So we'll be talking about the mathematical modeling of it today. So a similar example here. So if we give a car example, there are a lot of words come into our mind like wheel, freeway, radio, tire, whatever. Those are all kind of synonymous, but not exactly grammatically synonyms. So can we capture this kind of notion into some kind of mathematical form? So that was the early motivation for language model and a word vector, whatever we see today. So what people started doing at the time is people come up with a pointwise mutual information theory, or PMI, the very easy one to understand. People started looking at the joint probability. Okay, so let's say if we look at any corpus, we know there are words which co-appear. For example, shopping cart, for example, something of fast food, strong tea, or whatever. So can we look at the corpus and try to see how many times they co-appear, probability of PXY, divided by probability of the individual word. So what it will tell us, for example, shopping cart, how many times shopping individually occurred and cart individually occurred, and how many times they co-appear. If they co-appear all the times, then their connectedness with each other is much higher. If they are not, then their connectedness with each other is very, very low. So if we calculate PMI, simply how many times they co-appear, bigram frequency divided by frequency of the first word, frequency of the second word. So my fellow letters, fellow citizen, at home, United States, vice president, and so on and so forth. We can see all these numbers. The higher it is, the better it is. The lower it is, the bad it is. And also we might get negative PMI. So there are a lot of different kinds of PMI people use in research and NLP, positive PMI, PPMI, negative PMI, and so on, log PMI, and so on. But it's the simplest form of the PMI. So people started looking at this kind of conjunction, not only bigram, maybe trigram, quadgram, pentagram, and so on. But if we start increasing the size of n, we'll lose the context. Now people started looking at language modeling early 90s in a statistical way. So what is language modeling? It's a very simple one. So let's say I'm giving you this fill in the blanks, and we all did it in our school days. Which one will go to the first one and which one will go to the second one? If I ask you, what would be your answers?
Eight in the first one.
Eight is in the first one? Yes? Okay. And what for the second one? Audience.
Hate.
Hate in the second one. Then for the first one? For the first one, audience?
Play.
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 Okay. Okay, fine. So see how we know this. Possibly this function word is giving us a kind of clue which word will be going here. If it's a love and is here, possibly hate will not go here because that's a negative sentiment, and the reverse will not go here. But since it's a but, possibly hate will go here because it's a flip one. So language has a pattern in the word sequence, and if we can understand that, that's the rule of the language, and we can understand that by some kind of statistical meaning, and that's the form of language modeling. Okay, any one of you or maybe all of you have used the Smart Compose. Now it's become very common in Gmail, right? Is there anybody who did not use it? No one. So that's one motivation for language modeling, the simplest form. Whenever we type something in our mobile phone in Smart Compose, that's a language model. I can skip it. So here in Wipro Lab, we are actually working on language model for code mix languages, where if you type in nowadays in your mobile phone, people don't use single language, right? People use English, Penglish, or Tenglish, and so on. So, but anyway, due to the time scarcity, I cannot go over here. But what it does is basically
is prevalent.
predict the next word while you are typing in mixed language
तुम लोग hike, which
with certain probability. So that's a language model. So if we look at the language model research today and how good and bad this is in mobile phone, there's a nice example I got from from the Guinness Book of World Record. So what is the fastest typing human on earth? So there was a competition by Guinness Book of World Record Committee in 2011. This set of text has been given, and people are asked with the QWERTY keyboard to type this. And the fastest man on earth, whose name was Grace Park from US, who typed this in 56.57 seconds. Typically 4.66 character. But if you look at today's smart keyboard, whatever you use in your mobile phone, Plexi, Swift key, or Google, I don't know what you use for Indian languages, but typically any common man or woman can reach out this level of accuracy and fastness. So AI has gave us a lot of power. That's obviously language model. Sometimes it does error, and it does a lot of funny things. But let us skip this for the discussion. So okay, now let us formulate the language model with all this real life example. So statistical language modeling is nothing but a probability distribution, learning the probability distribution from a sequence of word given. So for example, learning the probability sequence of a given word sequence, word 1 to word m, the whole sequence. And if you can solve this problem, what we can do, we can apply into multiple problems like spelling correction. For example, if you let's say you are trying to make a spell corrector for Twitter, and you got a wordplay GOOT. Now it could be God, it could be good based on the context. And if you know the context well, you can predict it better. So spelling correction, machine translation, part of speech tagging, handwriting recognition. I don't know whether you have used any handwriting recognition, any pad or so. Sometimes R in small letters got misclassified as NI or something of that sort. So language model can fix it much better way, because it knows the context which will actually go there, information retrieval and so on. So language model in formulation, mathematically, what we are trying to understand, we are trying to understand this sequence and the probability of the whole sequence. So this is nothing but a summation of the probability of each word in a sequence. So for example, so we are trying to understand our pivot word, let's say WI, with a given sequence 1 to I minus 1. And we are making a summation from I1 to M. And we are just summing it over on the whole sequence. And that is giving us the probability. And that's the mathematical modeling or statistical modeling of, basic modeling of language modeling. So what we need to do, if we need to calculate this, we have to actually get the count of how many times I to I minus n minus 1 occur, and how many times I minus n minus 1 occur from I minus 1. So basically, let's say we have 4 words, how many times these 4 words occur together divided by how many times the previous 3 words occur together. So we will be getting a branching factor. So how many times, so what is the probability of this sequence, or what is the probability given this 3 word, this word will be appearing here. Now there's a problem here, there's a catch. So the problem is, let's say we are trying to predict the sequence of this one. What is this? Its water is so transparent that, and we are trying to predict whether the next word would be the or not, or many other words. So what we need to do, we have to get to our corpus in a sense, let's say whole Wikipedia we have downloaded, make a text version of it, and in text file we have saved it. It's a huge let's say 1 TB or 2 TB of file. So how many times this sequence occur, and how many times divide by how many times this one occur. So what do you think, how many times this will occur in Wikipedia? Any comment? Audience, any comment? What do you think? How many times this sequence will appear in whole Wikipedia?
Very rarely.
Very rarely. Right. So if it is very rarely appear or never appear, so what will be the probability of this? 0. And that will not solve our problem. So what people tried out at this point, they started breaking down into chain rules and multiplicative probability. So what they do, so they break it down into bigrams. Let's say, okay, we are not looking at the whole sequence. Let us look at the previous word, or maybe previous 2 words or previous 3 words. So our problem will be much more simpler. So probability of Wi, we are only looking at the probability of the previous word. So Wi minus 1. So this is an n-gram probability. So what is the base size of n? People have a lot of debates, lot of experimental truth. It depends on language, domain, problem, many other things. So you can understand if we start increasing the n, we will be getting lesser probabilities slowly. If we choose, smaller n, 1 or 2, we might not get a, very realistic number in terms of probability. So based on the, Markov assumption, the sequence of chain and probabilities, if we simplify this and only look at the previous event, might be we can solve the problem very closely in probability. It may not be very accurate, but it works. And that's the Markov assumption. I'm not going into the details of Markov assumption, how it comes, what is the history, and so on. But that's the simplest rule of Markov assumption being applied in language modeling. So what it comes? So we are looking into the count of how many times these 2 words occur. It could be 3 words, it could be 4 words, based on the size of n you are choosing for your language model, and how many times count of the previous word appear. And that's the probability we are getting for the bigrams. Now let's see in action how it will look. For example, let's say we have a tiny corpus of this kind, which has typical 6 sentences from Berkeley restaurants and so on. Now, if we try to formulate a language modeling problem as a kind of collocation matrix, so how many times this word appear after this word and so on and so forth. So for example, how many times 2 appear after 1? So maybe much higher than any other word. And how many times they appear single, singleton in the whole corpus, let's say this one. So how many times they co-appear 1 and 2 divided by the I. So we got some kind of probability numbers. Now this is the basic formulation of language modeling. Now if we look at any modeling today, either BERT or GPT or word vectors, everything starts from here. How? Let me explain, and slowly I will go and you will understand more. Now this co-occurrence matrix is then in future used as a vector. For example, I want to use a vectorification of a word like I. So I can take out this row and I can say, okay, this is my vector. And I can do some kind of mathematical formulation there. Either cosine similarity, Jacob coefficient, or matrix multiplication, or whatever I can do. And let's say I'm trying to get a representation of a sentence. Let's say I want to eat Chinese food. That's my sentences. I can take out all this vector and I can do some kind of average out, and I can say, okay, this is my representation of the sentence, and so on and so forth. So that's the basis of language model. Now this is telling us what? This is telling us very nice thing, that we are learning certain kind of co-occurrence logic by means of probability and statistics. But there is a problem here. The problem is we have a lot of zeros, and that creates a sparse matrix. And if you think about the scale of, let's say, Google and so on, it might not work. Will anyway come there. So there are a lot of such toolkit available. Have you seen the Google Engrams? Anybody? Or should I go there and talk about that?
Better, sir, if you can see some examples.
Sure. So let us try to go Google Engrams viewer. So this is typically the Google corpus, whatever Google collected so far, and based on the year, representation, and so on. So let's say Albert Einstein become very common in text after 1920s and so on. Sherlock Holmes, so on and so forth. So give me some, let's say, some bigram what you want to search here. Any 2 words, multi-word expression.
My
Language,
name,
Sorry,
my
language,
name,
I can't
language
hear.
modeling.
Language modeling. Okay. Let's say that's become this much and become very, very common now. Okay. What else?
Natural language processing.
Mhm. Okay, so you can search and play with this. What I want to show you is this is somewhere downloadable. I forget. There's a link here. Huh. So you can basically download all these, unigram, bigram, and trigram probabilities from the whole corpus Google has collected, and you can use it for your research or any other tool development. So this is completely free. You can download and you can see. Okay. So that's we build the basic case of language modeling. Now let us make it more complex over time. Okay, so before we make it more complex over time, let us see how we can evaluate language modeling. Because when you're talking about the statistical distribution of word, we have to, let's say we create some probability function, we create that co-occurrence matrix, we have to somehow evaluate this, right? Because otherwise we don't know how our language model is good or bad. So there are two basic ways of evaluating language models. One is intrinsic, one is extrinsic. So let me talk about extrinsic first. So extrinsic is very simple. You design some kind of statistical modeling of language, and you apply that learning probabilities into some some kind of applications. Next word prediction, spell correction, grammar correction, machine testing, and so on. And you see before plugging in the new language model and after plugging in, what is the accuracy difference. Now intrinsic. So intrinsic is, okay, I'm not actually applying my language model into certain application, but rather I'm trying to evaluate it by itself. So how? So let's say on an average, if I ask you, so let's say we have this vocabulary, and which one will go into first, which one will go into second, and which one will go into third. So what would be your answer? Audience. Audience, please. Nothing will go in the first.
There, mushroom,
Mushrooms, okay. For the second one,
the 33rd% of the US watch.
we don't have a choice, right?
Uh,
And the third one,
third one also
Not
not a
having a
choice.
choice, sir.
right? So see, this is the problem with the language model. For some cases, we have certain choices. For some cases, we really have no choices, and some cases, anything could sit there. So on an average, if you are trying to look at the probability of a sequence, and we are trying to understand the average of it, it's called perplexity. So probability of this sequence to the power -1 by n. So it will look like something of this form, square root of n and 1 by probability of the whole sequence. And by the previous slide, you have seen we can rewrite this as a sequence of of summation 1 to n probability of wi given the whole previous sequence. And by applying the Markov chain logic, looking at the just previous word, we can simplify this to this. Now that's the method to evaluate language modeling. Perplexity. Now, what does perplexity terminology means? So terminology means how confident your language model system is to tell you what would be the next word. how perplexed or confident your system is to tell you. And it typically gives a number in a range starting from 0 to few
One.
thousand, not one. It could be few thousand. So that's the way perplexity is being measured. Let me show you how in real life it looks. So typically, if we apply whatever basic language model we learned so far, if we simply apply that without having any added layer and so on, so typically trigram you will get higher perplexity, I mean lower perplexity 109, unigram you get higher perplexity and so on. So to read perplexity, higher the number is, the bad it is. The lower the number is, the better it is. So how I teach my student to read this. For example, maybe it's not mathematically correct, but you think this way. Let's say you have a fill in the blank situation, and you are trying to get the particular word will be sitting after this sequence of word, and you are looking at the whole vocabulary. Okay, and your whole vocabulary, let's say 30K words. So what you are trying to do, you are trying to calculate probability over all the 30,000 words, and whatever actually win the race, you are saying, okay, this word will be sitting here. So now say out of 30K, let's say your system is saying, okay, I'm quite confident about this 100 word. I don't know about the rest of it. So your system is giving you more specified choices, okay, from the 30K. And bigram is giving you 170, or unigram is giving you 962, and so on. So if we look at typically the perplexity of today's world using BERT, GPT, and so on and so forth. So let us have a look. I'm not sure you follow this this website, Paper with Code. Let us look at what is the typical perplexity of today's language modeling. And let's say on Wikitext, what is the typical range? So this is the leaderboard. So here, see, the test perplexity in the range of 10, 15, 16, 17, and so on. So basically read it this way. Your system, out of 30K or 50K words, your system is giving you, okay, I'm quite confident about these 10 words. Out of these 10 words, somebody will be sitting here. So that's the way you should read perplexity. Okay. So these are recent numbers, how the field is actually progressing. Now let us go ahead. Okay, and you can stop me anytime if you have any question. If you are not asking me questions, so I am getting a sense you are understanding everything.
Sure, sir.
Okay, now there's a catch here. So somebody at the beginning, when I was asking, so he said after the GIFS law, there's a problem with the rare word, out of vocabulary word, and many other words, right? And that's the challenge of language, because we can never be able to create a dictionary which is complete, because every day new words are coming. There are lots of named entities, unlimited new word. Even Google encounter, according to their statistics, 25% new word every day in a Google scale. So, and that's the challenge of language modeling. So what we can do, how to handle the unseen word, and how to do it. So we already talked about this reliability versus discrimination. The larger the n is, we get the better discrimination, but smaller the n is, we might not get the better reliability. So at this point of time, when people design the basic language model, people start encountering problem with the out of vocabulary word and unseen words. So now going back to the basic, GIFS law. What GIFS law said us? So no matter what the language is, no matter what the domain is, we will be always getting a particular, distribution. So if we believe GIFS law is correct, and we will be always getting that Pareto optimal font in a language, so whatever new sequence we see, we can restore it to that particular pattern, and we can fit it there. And that's the notion of smoothing. So let's say we are trying to calculate the distribution of word in a given corpus, and we got something of that sort. Now, since GIFS law told us, I mean, this pattern will not look like this pattern will look like something of this sort in a Pareto optimal font or GIFS pattern or whatever you say. So can we restore this distribution in some way or other so that it appears in that particular pattern? Because we believe that will always happen. no matter the languages. And if we try to do that, so we can possibly somehow still some probability from the highly awkward word, typically words like a and the and whatever words which are not carrying much meaning but kind of fillers in a language, the function words, and we try to give more probability with some unseen word and so on. So the notion of smoothing comes from here. So why smoothing? So we got some normal probability distribution from a corpus and we are trying to smooth it up based on some predefined pre-notion law pattern, which is Gibbs law. So that's smoothing. So now, what is the basic smoothing technique we have? So that's called add one or Laplace smoothing. It's a very simple one. What we are saying, okay, let's say we encounter some word which we never seen in our corpus. So what we are saying, okay, well, let's say we give one. We say in our corpus it appear only one time. So we do a plus one because otherwise it will be zero. So while we are putting plus one, we have to distribute the probability load based on the whole distribution of the word. So we are dividing it by the total number of vocabulary. So phi. So what we are getting, so you remember this was our co-occurrence matrix, and instead of 0 we are putting a lot of 1 here. So it's not sparse matrix, although this is sparse, but we have some kind of numbers here, and we are putting the distribution here by dividing the phi. So we are getting a lot of small numbers. So and we are restoring the Gibbs distribution in some way or other. So okay, so this is the smoothing technique. Now this is a very simple one. It does not nobody use it today. It was from the historical language modeling where people used to work in 80s and 90s. And then you can do a lot more experiment with bigram, trigram, add one, or something of that sort. There are a lot of smoothing techniques available in the history of NLP. During the whole 90s, people worked on different kind of smoothing techniques. Laplace or advanced smoothing is just a basic one. There are a lot of other techniques, good Turing, Naser-Neikart, and so on. If you are interested, you can go into this link and see. You can find possibly 15 different kind of smoothing techniques. So the way you should look at smoothing is language always comes in a new form, new syntactic distribution, new word order, and we can never estimate the correct probability. So smoothing is a technique to post-fix the probability distribution you learn. So I give a pause here. Any question here? I would like to answer. No. So let us go ahead. Now, what happened? We hit the web scale and Google born. And then things started changing. So I can skip this one video possibly. The problem started becoming, I will go a little fast forward now because I have to move towards the modern language modeling. So the problem at the Google scale happens, we have a really large scale of data and we have to find out, given a query, what is the right document. So that is huge scale. I skip this. So what people initial days started is I typically when I teach this I say searching is solve problem like binary search tree or other kind of searching technique was there. So then why people need to reinvent a searching technique at this stage? Because of the scale. It's a huge scale problem. So the basic thing people started doing is people put it 1 and 0 in a kind of index table. Let's say we are trying to create an index table from Julius Caesar, all the books, and we are saying, okay, these are the words appear, if it is appear 1, if otherwise 0. Now you can imagine if you go for the web scale of Google, the number of columns will be in trillions and also possibly number of rows would be in millions in a language. And processing this kind of huge matrix, or if you think you are taking out one row and saying this is my vector representation of word, might be very difficult. So it will not work out. So I jumped this. People talked about TF-IDF. I'm quite sure you know TF-IDF, so I'm skipping it. So at Google scale, people started doing the same thing of language model, PMI, or joint distribution, and so on. For example, Angry Bird, and how many times they co-appear in a document level. People started calling it at that age, like mid 90s, called information extraction age. So people used to call it correlation coefficients. So this is nothing but simply this formulation. How many times they co-appear the document label, we can calculate and we can understand what is the relation of these two words. Anybody have a question? Somebody saying something. No. Okay. Let me skip this. So the problem we hit at the web scale is the size uh, of the vocabulary and the size of the document, and this is the beginning of the invention or the way of distribution semantics, or what to say. So I'm quite sure you have heard about singular value decomposition, but how it actually connected to the representation and modern language modeling, let me take you there. So the problem here was, as I showed you in a Google scale, the vector size was huge, either for document or for word. So somehow people wanted to squeeze it up in certain dimensions so that the calculation has to be really fast. So people started looking at matrix factorization model. The simplest one is a singular value decomposition, so that they can squeeze the factor in certain way, and also they wanted to preserve the notion of this distributional semantics. So what singular value decomposition is very simple. Given a matrix, it will break down the matrix into three different matrices. One is U, one is sigma, one is V. U is this one, vertical one. Sigma is the diagonal one, and this is kind of horizontal one. So if you don't understand, uh, you can ask me question. This part would be a little trickier. So let's say, take this example and try to understand. Although this is not an NLP example, I took this example from typically, let's say, movie recommendation. I'm quite sure you have some kind of OTT platform subscription nowadays, either Netflix or something else. Okay, now let's say I'm working for Netflix and I'm trying to understand what are the preferences of given user in particular movie genre. Okay, so here in this matrix, this row represent one user, and this row column represent kind of movie name. So I'm trying to understand, given a user, how he or she rate this movie. Let's say Matrix, Alien, Serenity, Casablanca, and something of this sort. So if you look at this portion of the matrix, typically these are the people who actually look, and love sci-fi movies. And if you look at this portion of the matrix, the people actually love the romantic movies and so on. So now the challenge and what matrix factorization does, it breaks down into three matrices. One is U and this one is U. Typically the concept matrix, this is sigma. So this is telling us what is the weightage of particular columns here and columns here. And this is typically the V transpose is telling us typical importance of each column. So here, if we can break it down into these three matrices, what might happen? What would be the benefit? So let me show you the example. Again, I will come back here. So the problem of distribution semantics or co-occurrence matrix having is, it was, I mean, before this singular value decomposition applied to language models and so on, it was easier to get the distribution semantics. For example, car, wheel, and etc. But there are words which are synonymous. For example, human and user, or let's say machine and system. Those words never co-appear because they are kind of synonymous in a modern corpus. So if human appear, user does not appear. If machine appears, system does not appear. So to get this kind of notion, SBD actually helped a lot to get this latent semantic space, and the term latent semantic space actually born at this time. So how? Let us look at this example, and then I'll again go back and give a pause here. So Let's say we are trying to solve this problem. What is the problem? Let's say we have 3 documents. I hope you can see this. Otherwise, I can maximize this. Let's say we have 3 documents of this sort: shipment of gold damage in fire and so on. So document 1, 2, 3, and we have a kind of query we have to rank. So this is our query. Let's say gold, silver, truck is our query, and we have to rank the document D1 and D2 and D3 into certain kind of ranking function. So what without any kind of singular value decomposition we can do, we can create an index matrix of this sort. So what this says, this is my corpus. So how many unique word appear here? Let's say this is my unique word. How many documents we have? D1, D2, and D3. Typically, simply Google formulation of the problem index table. So we are putting 1 and 0. If this word appear in document 1, we put 1, otherwise 0. So we represent this whole document collection into 1-0 format. So this is my index table or matrix. And I'm also representing my query here into this 1 and 0 format. So only 3 words appear: gold, silver, truck. So 3 ones, otherwise 0. So this is my problem formulation. Now, don't think problem formulation only this small tiny data set. This is a problem formulation for Google, and which has a trillion documents and a million word form. And in a given second, possibly millions of users are coming and searching their queries, and they have to create the results in a nanoseconds. That's the challenges. And if this matrix is huge, then doing a lot of computation become very tough. So now the challenge is, can we apply any kind of matrix factorization or singular value decomposition kind of technique so that we can break it down into smaller matrices? So what could be done? We can take this matrix and break it down into these 3 matrices: U, sigma, and V transpose. And we are doing that. So this is our U, and this is our sigma, and this is our V, and the transpose of it. So we have 3 matrices. And now we are saying, okay, this is typically my document vectors. I'm not taking this, and this is telling my weightage of that. So what I'm doing, I'm taking this matrix out from here. So sorry, I said this is not this one. This one. Sigma is telling me the importance of each column. Okay. So if you look at diagonal matrix, this is 4, this is 2, and this is 1. So that means this last column may not be that much useful, and for V, the last row is not that much useful. So we cut down 1 dimension here. So we are saying, okay, this is my document matrix, the first 2 columns. So we take out the first 2 columns as a squeeze dimension, and we are taking out the last row of this one, cut down, and we are saying, okay, these are my new vectors for the documents. Okay, so this is my new vector for the document, and I can simply apply the same for the query. Given a query vector, I can again break it down into the singular value decomposition, and I can get a squeezed representation of the query. So now see, instead of a bigger matrix or a vector, high dimensional, sorry, I have a much squeezed version of the low dimension space of query and low dimension space of documents. And if I apply the simple similarity, for example, cosine similarity between document and vector, it could be shown very easily that I can get the same result what I was getting if I don't squeeze up the whole matrix into singular value decomposition, and the result would be same. And that's the bingo situation in late 90s when people start applying singular value decomposition. So what we get from this whole exercise is we start getting a low dimension vectors which still perform the good of the language representation, and also gives us kind of meaningful representation of similar word like human, user, or machine and system. So I give a pause here, and this is a little trickier, so feel free to ask me any question you have in mind.
So, excusing this matrix, I mean, how far will go? I mean,
Okay.
how many dimensions, and how will decide the dimension?
Right. So that's a nice question. So there is no such fixed dimension. So it depends on how fast versus how accurate you want to be. So see, if you see this sigma matrix, which is a kind of importance matrix, if you cut down one dimension, you are still getting a better results. So people did a lot of experiments in that information retrieval or information extraction era. So what is the base dimension to be? So now if you look at today's word to vec as well, okay, I'm not sure whether you know it or not. So word to vec representation actually available in various dimensions, 100, 300, 700. So the idea is the higher dimension will give you more information, the lower dimension will give you less information. Now, if you are applying those word vectors in a difficult task in NLP, for example, machine translation, which is a much more difficult task than simply, let's say, document classification, or let's say sentiment analysis, maybe a lower dimensional problem. So if you are applying it to a tougher problem like machine translation, you use the higher dimension, but it also costs you more computing power. But if you are using it for a lower purpose work like document classification only, then use the lower dimension, but it will also be much cheaper for you in type of computation.
Okay, sir. So basically, it depends on tasks.
Depends on task. Yes.
Okay, sir. Thank you.
Yeah. I expect more question here. Please feel free to ask, because after this I will go in a huge speed. No more question? Everybody understood singular value decomposition? Did you do it in other courses, singular value decomposition?
We attended a few lectures on this previously.
Sure. Okay. Now, what happened after this? Word vector comes. So there's a nice paper in 2016 ACL that if we apply simple statistical language modeling using singular value decomposition, and whatever word to vec is giving us is not much different. So actually, that's the time when word vectors actually born. So what Makarov did during his PhD, he started formulating this problem given a neural network and tried to predict the next word in a sequence. If you download the word vector nowadays, they might look like this. And if you're wondering what they represent, there is no answer for that. It's not human readable. It's a high dimensional vector, and I will skip all these things because of time. So I can possibly jump directly into. So then globe, and then Elmo and various other things came out. People started talking about the bias of word vector, gender bias, and so on. Now let me directly go to this section, sentence embedding. Okay. So what is sentence embedding, and what does it mean for language model? So as I said, that there are a lot of sentence level classification problem in NLP, and if you're trying to represent a sentence in a given fixed size word vector or fixed size vector, then we have to understand how the words are actually influencing each other present in the sentence level. So during the neural network era, people started coming out with the RNN kind of methodology. So which is working in a kind of time step. So what we are doing at each time steps, we are giving a word vector input, and then we have a weightage coming from the previous layer, and we are computing some kind of non-linearity here, and we are passing it there, and also passing it there. I mean, at up if somebody wants to do some process here. So that's the kind of typical RNN architecture. Let me go little. So the simple thing we could have done for sentence level embedding is we could have taken all the word embedding. I mean, let's say all kind of let's say we do a singular value decomposition, and we fix the size of the word vector from a very simple statistical language modeling, or let's say word to vec of Nikolov, or let's say globe from Manning, or something else. So all kind of word vectors available with us, and we take all the word vectors and try to calculate a mean out of them. So how many words are there, and simply do that, and we got a fixed size vector for the sentence representation. That's the simplest one we can do, right? So do you think there is a problem here if we do that?
Sir, is it, high computational power required?
No, it's
I
not,
mean,
right? It's a simple one, right? We just take, let's say you have a sentence, I don't like chocolate, and how many words are there? So 3 words, right? 4 words. So 4 words, you just take 4 word vector, from your previously computed vectors, and just average them. Divide by 4. The simplest one, right?
But sentence length is not unique one, sir.
So we can fix it, right? So typically what is being done in RNN kind of setup, if you look at, so not in the language modeling setup, but if you look at the RNN era, RD neural network era, so we can fix out a fixed length of sentence. So we say, okay, typical, let's say I'm working with Twitter sentiment analysis. So I say, okay, typical length of sentence is 10. Anything less than that, I will pad, I will put 0 for those words. Anything more than that, I will drop. It's a 10. My problem is solved. Do you see any problem here? No problem? There's a problem. The problem is the dependency of words. For example, in language, we have longer dependencies. The typical example Manning gives in his online class, if anybody of you have seen the lectures. For example, the computer I bought last year, used it several months, and blah blah blah, crashed. Now this crash and the computer has a link. And if we do this kind of average out between word vectors, the relation between them are lost. And that will not help us in the long run to do any kind of complex NLP task. And for example, I don't like chocolate. Here, the like is getting modified by don't, but not chocolate as such by I. So there are interdependencies, and that need to be learned. So RNN, there are different kinds of RNN for different kinds of problem. So typically when we do sentence classification kind of problem or sentence level problem, what RNN does is we keep giving one input and keep doing this non-linearity computation here, and at the end of the story we got some vector out. So more and more we go deeper into the deep learning era, and more this kind of problems started coming. We started realizing that we need to have a better sentence representation in terms of language modeling. So also typical, let's say, machine translation, encoder decoder problem. So you have an input looking like something of that sort, then you start decoding it, and then you start getting the target sentence until unless you hit certain threshold to stop it. So if we again compare it with the previous era of statistical language modeling, so what we used to do, we used to calculate bigram probability in sequence, in a multiply fashion. Okay, so we look at what is the probability of the sequence. We start doing this. Typically, we not used to do that. We used to use log to avoid some kind of underflow overflow. So can we do the similar pattern here? So let me talk about this one. So when we're designing a language model, what we are trying to do, we are trying to actually predict the next word and the probability of next word over all the vocabulary size. So let's say we are starting with the word which is sentence start marker, and then we are trying to predict what would be the next words. So let's say we have a 30K vocabulary, we are predicting all the probability over all the 30K words. Now, if this is the first word, what will be the next word? What will be the next word? So this is the problem appear in the neural network setup of language modeling, and this is one of the reasons actually why neural network was not very successful in early 90s, because this actually create a very large competition problem, and we have to hit the greedy search or beam search for this kind of setup. So it multiplies the complexity. So to do that, what in modern times I talked about this. So to get the notion of the interdependency between words, so what in typical neural language modeling people started looking at the very beginning. So they said, okay, all words are not equally important. So what we can do, we can put one softmax function on top of every word. So what it will learn? So it will tell me, let's say this sentence has 10 words, and which word has more, influence on this word while we are calculating the meaning. So we can give some kind of soft distribution, and we can learn that while we are doing the forward and backward propagation, while we are training the recurrent neural network. So softmax become very popular, and then people come out with hierarchical softmax function and so on and so forth. So now this is the beginning of the attention model. So if you read the famous paper Attention All You Need by Google, so this is the beginning. But the problem here was calculating this many softmax in a longer sentences was difficult. But it shows the very promising results for various tasks which is semantically complex. For example, sentiment analysis. And in sentiment analysis, what happened? Typically, one word changed the meaning of the whole sentence, the negations and the negative one, and so on. Then people started talking about contextualized meaning of word, not only predefined or pre-calculated word vectors. People say, let's say we have two words like two banks, bank and bank, but these two banks are different. But if we look at the formal word to vec or globe model, we don't have two representation for polysemous word, which word has multiple meaning. So what is the solution for that? WSD was a problem, or word sense disambiguation. So people said, okay, fine, we have a simple magic here to do. So what we'll do, we'll take a word vector which is pre-calculated, we'll take out the word vector, and we'll average it out in some way or other by looking at the nearby content. Let's say two previous one and two next one, and the new representation we learn, that's the kind of my context dependent representation of word vector. And people start applying this into multiple application, and people got significantly good result. And that's the notion of Elmo comes in. And that's built the case of BERT when Google come out with it. And then it started. BERT, GPT, and MTT, and so on. So now if we look at the NLP age, if we look at any company, so there's a fight going on between BERT, GPT, and language model. And this is the paper came out in late 2018. So what are the things that actually BERT get into? So number one, the basic assumption BERT coming up with, language understanding is not unidirectional. If we look at the era of statistical language modeling, we have been mostly looking at the language modeling from left to right, not right to left. But BERT says it's both directional. So we can actually have a neural network which can look at the both sides and try to get some kind of average out, and it will give us more stronger language model than ever been built. They come unidirectional model, fine. Then they also come up with the mask model. This is very similar to what we have in the statistical era, but instead of predicting all the next words.
Actually, sir.
Yes.
But how the language model will work in reverse direction?
Okay, so let's say the man went to buy a milk, right? So we have been learning the probability of these two words, the man went to the, right, so far. But
Okay.
BERT assumption says no, Also, if you look at reverse, there is also certain sequence: milk of a by. So it also has certain kind of predefined pattern. It's not happening randomly. So if we learn that reverse direction as well, and if we get the representation of both the learning and merge them in some kind of way, we can get a better representation.
Okay.
Understandable?
Yes, sir.
Okay. Now they come up with a mask model. It's very simple. So instead of calculating probability of each word, they randomly delete some word and ask the language model to predict. So that's become a new norm of language model evaluation, and that is helpful for when you have a large language model. They also uh, they also uh, make a difficult task to attempt. So let's say next sentence prediction. So instead of next word prediction, can a language model which is trained on a huge data set, huge data set in a sense, let's say few billion word order and few TB of data. Maybe not BART did not try TB of data. Maybe GPT-3 came out with a certain 120 TB data or something of that sort. So can language model also predict the next word, next sentence? So that also BERT tried, and then during that time when BERT came out, people already started looking at multi-layer, stacked approach. So instead of layer one, so the idea was if you increase the layer, vertically up, so possibly you will get more information and more dependency, different kind of dependency. It will be learning. So although at the initial age people started just increasing the number of layers, and it was learning something or was getting better results, people did not know what it is learning. Then when BERT came out, and there's a paper from Dipanjan possibly in 2017 ACL, so that actually describe and visualize what are the different layers of language model learning. So maybe the first layer is learning the word sequence, second is POS, third is syntactic rules, fourth is semantics, and fifth is pragmatics, of something of that sort. So this is BERT, and I can possibly pause here and open for question here. So it's a free to talk session. If you have question, discussion, whatever comes into your mind, you can just talk.
So participants, anyone who wants to ask question?
Hello, sir. Uh,
Yeah,
Sir,
please go ahead.
there are language pre-trained word embeddings like BERT, LMO, OpenGPT, whichever you have talked about. Can you tell me the which one will be the better one, which is working? We can compare between them.
Okay, sure. So your question is manifold. Number one, word embedding and sentence embedding are different. Word embedding is giving you distribution semantics representation of words. Sentence embedding is giving you a representation vector for the whole sentence. Okay. Now, which one is better is very difficult to tell you. So, in every 1 or 2 months, there is a new paper from XYZ company, either Facebook or Microsoft or Google or any other researcher who are claiming my model is better than yours. So, according to the last result of GPT-3, which has been trained on typically 123 TB of data, and it ran for a month with their setup, and which cost them $1 million at least to train the system, was the best one. But unfortunately, GPT-3 is not publicly available. Microsoft bought the exclusive license of it, so that's not there to uh, experiment with. Now there's another one called ExcelNet, which is a reasonably better one. So the Jan LeCun one, who created that ExcelNet from Facebook Research. He's also a chief scientist in Facebook Research. So, but the ExcelNet problem is this is the kind of library available for ExcelNet is very difficult to use. So the best one, typically people use open source and everybody use for practice is BERT, the Google one, and which is really usable, very easy to use, very easy to port, and so on. So that's my elaborate answer is.
Sir, somehow we know about word embedding, but I think the recent version, I mean the sentence embedding, it is a little bit harder compared to, I mean much more harder compared to the word embedding. So,
Right.
what are the state of the art results currently in sentence embedding?
Okay, so there are a lot. So if you look at every year NLP conferences, there is a new method coming in for sentence embedding. So according to my understanding and my recent updates, if you look at Google Sentence Encoder, the Universal Sentence Encoder, BERT, and few others are the latest one and mostly useful.
Okay, sir. Thank you.
So, is there any general guidelines which we can follow to identify that which model would be better for a particular type of the problem?
The answer is no.
No, no.
So yeah, so basically you go to this website or maybe similar website, and you look at a particular task of, let's say this is all different kinds of natural language processing tasks.
That's a big challenge, sir.
No, see, okay, so hold on. So let's say this is machine translation, question answering, language modeling, text classification, sentiment analysis, blah blah blah. So the different kind of task, and let's say you want to look at, let's say, name entity recognition, and
Yes.
you go here and you are trying to see, okay, what is the accuracy trend in particular here, and then you go and see which word embedding they're using, and you can do this kind of analysis when you are doing certain research. So maybe that would be a little helpful for you.
One more time, can you explain, sir? I couldn't get.
Okay, so this is a chart you can see, right? This is more name entity recognition. What is the typical accuracy range till July 20? Okay, where we stand today, and all the papers and all the codes and system are available here. Now your question is, okay, let's say what they're using. They're using what to pay Globe or Elmo.
Uh, I am working for the machine translation.
Okay, you are working with the machine translation. So let's go there. Let's let's go to machine translation. Okay, machine translation. Go here, and this is the trend. I don't know which language you are working with. Let's say no, no, fine. Let's say we look at English German case.
Okay.
So let's say English German. This is the kind of blue score possibly till the July 18 or something of that sort. So all the papers are available. Now you see which embedding people are using, either Globe or Word2Vec or Elmo or what. So you can make a survey and then you can decide on that, because ultimately all depends on the empirical analysis, right? I mean, you can't say without knowing okay, this method is better than this method. Ultimately, all are empirical.
Analysis is required at all.
Yeah, yeah. So analysis you can get here, or maybe there are some similar websites also.
Sir, excuse me, sir.
Yeah, yeah.
Sir, should really word embeddings are going to be being show some effect over the accuracy of the model?
Yeah, absolutely, yes.
It's not depend upon the architecture of the system.
See, everything, right? So word embedding is the representation of word. So if you are using a bad representation of word, no matter how good your algorithm is, not going to work, right?
Okay. So better word representation will give rise to the better accurate result of our algorithm.
Absolutely, yes.
So then, in the context of test classification, so how word embeddings is make differs with the sentence level embeddings. So
Okay.
which one is?
No. So text classification has several kinds, right? So what kind of classification you are doing? So if you are doing a document classification, whether this given document is a course document or is a news document, then it's not a sentence embedding problem. You don't need it. But let's say if you are doing a sentiment analysis kind of problem, then you need a sentence embedding. If you are
Sir,
just, huh,
for example, I have a Stack Overflow data set is there. So it may be contains list of questions are. So each question may be related to one particular subject.
right. So
So
it's a
like that.
okay, it's a sentence level problem, right?
Yes, 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 yes.
It's a document level problem. Then you need a sentence embedding.
Okay, okay, okay. So if the test classification is done based on sentence level sentence level embeddings, so then it will give the better result when compared with the word embeddings.
No, no, hold on. What is the question? Word embedding are needed to calculate the sentence embedding. So there is no either or. You need, if you need sentence embedding, you need word embedding as well, right?
Yeah, okay. Now my question is, instead of using the word embeddings in the text
No, no,
classification,
no, no. How
if we go
can
for
you? No, no, no. Can you write a sentence without word? You can't, right?
yes,
So if you are calculating a sentence embedding and fine tuning it for your particular purpose, you need one embedding. But you are asking me a question, I should use, word embedding or sentence embedding. So
yes, yes.
my point is you cannot use sentence embedding without word embedding.
Okay, okay. So sentence level embedding is next level to the word embedding.
Absolutely, yes.
Okay, okay, okay.
Any more
Sir,
questions?
yeah, sir, I think there is no more questions from the participants.
So okay, then we are done.
Yeah, yeah. Thank you so much, sir. That was really an interesting session about language modeling and NLP. And thank you, participants, for making the session interactive. And we'll meet tomorrow at 5:30 for.
Sir, one last question is there,
Yeah,
sir,
yeah.
Amitav sir.
Sure, sure. Go on.
Sir, where we, if we want to see the implementation of all these things in practically, so is there any references to consider?
Yeah, so I suggest you go to this Paper with Code website. This is
Okay,
one of the best comprehensive I know. Maybe there are many, I don't know. So this
okay,
is
sir.
very comprehensive, and you can go here. You can get all the codes, all the papers, all the resources available.
Okay, sir. Okay, sir. Thank you for very much for suggesting this.
Sure.
Hello.
Yeah.
Hello.
Yeah. Yeah.
No,
Hi.
not sir. I'm asking to the coordinator.
Oh,
Oh,
okay.
yes, sir. Yes, sir.
Any process for attendance marking?
Oh, yeah, yes, sir. We are recording the attendances.
Where?
Sir, in a sheet, we are doing the attendance.
Okay, so
Okay.
we have some kind of plugin so that we can record the attendance time to time. We do the
Okay,
interval
sir.
of
Okay.
yes. Anyway, I think now we should thank the speaker again for a very interesting talk, and I would like to ask the participants to join the session tomorrow at 5:30 again. So we can leave the meeting now.
Thank you.
Thank you, sir. To you also.